Hello, everyone. Welcome to today's live stream. Um, Here today we have Willem Nielsen talking about 50 years of game of life, engineering, and
Uh,
innovation.
Dugan, you're muted.
Oh,
I don't know if you're supposed to be.
sorry, I was muted on the meeting, but not online. So everyone, the video heard it, but anyway, we'll go ahead. Willem, go ahead.
Okay, thanks, Dugan. Yeah, so let me just share my screen. Okay, uh, show you 1 second. Okay, yeah, so I'm just going to be talking about the recent work I helped Stephen Wolfram with on a minimal or looking at a case study of engineering and innovation using the game of life. So um, this is an example of one example of what the game of life is. And basically, it's just a 2D cellular automata. So you have a discrete grid of cells, and you can run that, and you run those cells. We think about it like time. So you can represent that as a video, like this one. And this particular one is called a glider gun, and we'll talk more about the different kind of inventions that have been created in the game of life. But that's kind of one way. Oops, that's one way to represent. Sorry, there we go. But it's helpful to use other kind of visualizations. And so I'm just going to walk you through those as some background. So basically in this left panel here, we have what's called a history plot. And so what that means is just um, you, instead of, showing it as a video, you just show the time kind of as trails of colors. So yeah, we can think about like the trails represent where the parts of the system were, at a few steps before. And then we can also use like 3D. So in the second panel, we can see like it's like 2D, but then time, it's like the video, but instead of you have time going down. So as you evolve the system, you go downwards and then you get this nice 3D visualization. So you can see the history of uh, the the whole system, which is helpful in conceptualizing or understanding what's going on. And this third panel is just it's like the 3D plot from the side, basically. So yeah, those are kind of the visualizations that we'll use. And so there's been a lot of inventions in the game of life, and it's been like over 50 years of kind of people, designing these patterns to, achieve different objectives. So these are some of the basic ones. So we have the blinker, which just oscillates, kind of flips back and forth. The traffic light and all these other ones. Yeah, so these are some of the basic constructions. And then, so kind of more complicated. So these ones, they kind of just stay in the same place or oscillate. Um, So these ones actually move across the grid of cells. So yeah, they're called spaceships.
And um, kind
Mhm.
of get a sense for how fast everything, like the speed of the gliders, by the slope of those plots.
Yeah. That's a good question. I mean, I can show you just a video. It's probably helpful. Yeah, so like these are gliders moving. I mean, it obviously depends on the frame rate, but oops, sorry, you can't see that.
Or full screen, I guess.
Yeah. Yeah, so these are gliders moving.
Mm-hmm.
Um, yeah, I mean, what more specifically, what do you mean about the speed? Like,
I mean, different gliders have different velocities, or
I
they
see.
take like a number of different the number of iterations before they show up again.
Right. Okay, yeah. So I think we can see that. Yeah, I mean, you can see like if we just look at this guy, oops. Yeah, maybe after we can write some quick code to look at the 3D versions of these, but it looks like this one just from the 3D plots, just kind of I feel like the speed is just the angle of the 3D plot. So I would say
So are
it
you
looks
sharing
like
your Chrome window again?
sorry. I can just do my whole screen. Yeah, so this one looks like the heavyweight spaceship is moving a bit faster, I think, but yeah, we should check that after. Yeah, so another kind of those are kind of the basic, the oscillators, and then the what's called still lifes are just they stay in the same place. But these are called glider guns. So they basically, instead of just moving back and forth, they actually create new structures and produce growth. So this is an example of that, and you can see the like the glider shooting off of it, and that was what the video. This is a the video I just showed was another example of the glider gun.
Okay. And all that
Yeah, and you can
machinery
see
like
it shoot.
stays in place while it generates gliders that like shoot out.
Exactly, yeah. So these parts are staying in. Well, for this one, I mean, they're moving. So these parts in this section are oscillating, but this one is moving across the frame.
Hmm.
Yeah. Okay. So now that I've given a little bit of a sense of what's been made in the game of life, we can talk about what we actually did to study, the system. So one of the things we really focused on is called modularity, and what we do is we just look at which parts of the system are causally separated. So meaning, you know, this like this what's called an R pentamino. If it's two, cells away from the other piece of the system, then it means that it can't influence, the the nature of that pattern or the design of that pattern doesn't influence the other patterns in that particular time step. So when that happens, we kind of separate them with edges. So like, from this frame to this frame, there's kind of now five distinct causally separated parts. And that gives us an indication of how much of the system is modular, meaning you can just run it on its own, and how much is dependent on the different parts. And what's interesting is with the engineered systems, so Stephen kind of makes this distinction, and this is a like a kind of in the same graph, but without showing the actual patterns. And what's interesting is Stephen makes this distinction between patterns that are engineered and discovered. So patterns that are engineered, we see them as more modular. Um, and when I say engineered, I mean explicitly by a human. So it's like they kind of design the parts to get it to do what they want. In this case, these are oscillators. So they're trying to get this pattern to repeat at some, I think this is a period 9. We can just see. Yeah,
What was the thing on the left on the previous screen with the sort of like red graphs running to the side? The screen before this one. But yeah, this one
okay,
over
yeah.
here.
So we're just highlighting the parts of the array that are far enough apart to be causally separated. So in this second frame, the distance between the two parts is 2 cells. So that means that they can't influence each other. So we show that as separate parts. Does that make sense?
I see. So the first frame is they're all um, they can't be separated. The first frame cannot be separated. The second one can.
Exactly. Yeah.
The area of influence,
Uh-huh.
what the red is showing, something like that. Yeah.
Yeah.
Is it possible that we can look at an animation of what's going on here?
I'd have to do a little bit of coding for that. So maybe afterwards,
Okay.
or we could just try it here. Let's see. We could just.
We could also just pull up the Game of Life index. I think there's like a website that has all of these things.
Oh yeah, that's actually a good
default.
point. Let's just try that.
Perhaps Eric could bring up that one specifically for us.
Yeah, we could try that. Hmm. That's not very helpful. Just some bees. Uh, maybe if
Have a
I,
name? I'll look for it in the background.
yeah, it's called worker bee.
Oh, okay, we'll check it out.
Yeah, maybe if I just do this.
Initialize ID. Yeah.
Yeah, there we go.
Okay. So that's
A little fast. Maybe just the frames would be helpful too. Yeah, these are the frames.
yeah. You can hit that with list animate. I
Yeah,
think.
let's try it.
And now you can scroll through. Okay, that's better. Cool. So
Yeah,
it
okay,
has
so
like a blob in the middle that spins off some things and some blockers on either side on the four corners that like keep it contained.
mhm,
Okay. So it's made of like 5 components essentially. That's how it's engineered.
right.
And when you split the diagram up into its components, we can see that. Like that's what
It would be
the
interesting to see like just this middle part. Let's see if we can do that. What happens without the pentomino, you know? Hmm. I don't know how to do that. Yes, it would be, yeah, maybe after.
Mhm.
Okay, so maybe I should just keep going here.
Sure.
Um, yeah, so we make this distinction between engineered and explicitly engineered by a human and discovered by a computer algorithm. And what's interesting is the ones that are discovered by a computer algorithm tend to have less modularity than the ones engineered by humans, which makes sense because it's like when humans are making things, they kind of need to have parts that they understand what they're doing to get it to do the thing that they want it to do. So for it would be very hard to find, for example, this one found by search, it would be very hard for a human to be able to tell that that's going to have a period 9 oscillation. And the graphs are kind of an indication of the modularity. So this one found by search kind of just has a blob um, evolving over time. And these ones, engineered are much more modular across time and split into different parts and so on.
Cool. I love those diagrams.
Yeah, these are nice. And we can compare that because it's like a nice and simple model and it's just bits. We can compare that with adaptive evolution. So what this is doing is it's just changing the initial conditions of the game, still using the game of life rules, but changing the initial conditions bit by bit and looking for patterns that give a longer halting length. So these ones, they're labeled with the length that they halt at. And what's cool is that these ones kind of look more biological or like a little more fuzzier or complicated than the engineered systems and also less modular. Yeah. And this is just, oops, some more examples of
Do they
systems.
do they happen to be any more modular than the ones that are just um like not the engineered ones, but the discovered ones?
Discovered. Yeah, I don't think so actually. And that's an interesting question. I mean, we've done experiments trying to determine from the rules, can you determine if it's evolved or found by search? And it's pretty hard. But maybe we can also, that's another thing to look at after is the bounding box or the modular graphs, I should say, of these adapted algorithm of these adapted patterns. Okay, so kind of zooming out, we can look at not just the specific systems, but we can also look at how they improve or change over many years as a kind of model of what happens in innovation in things like tech. And so what's interesting is you can see that there's kind of waves of activity similar to how different for example, scientific fields have fashions. So like in 2020, this big spike is because of or presumably because of, COVID, and a lot of people just had a lot more time on their hands to run simulations, I think, was what we kind of came to the conclusion. But yeah, it's just nice to see waves of activity. And then we can look at things like winner take all effects. So this is showing the distribution of discoveries across different people. And what's interesting is that we see, most of the discoveries come from a select few individuals. So I think about it kind of similar to how, something like wealth can concentrate among a select group, because it's like once you've made, 100, once you've made 50 discoveries, the next 50 is a lot easier, or, it's more likely that you'll make those discoveries because, you obviously are good at discovering things. You know, that's a potential reason, or just the way I think about it. But yeah, and then we can also see the activity for these discoveries. So, I mean, kind of similar to the waves of activity plot before, we see the different people have kind of different like eras where they are making discoveries. Yeah, and some of these people we actually talked to like
You want to give that?
insight. Go ahead.
You want to give that a scroll down just so that everyone's name
Oh,
is
yeah.
showing it as well. Yeah.
Yeah.
Saw Conway near the top.
Yeah, on Edsfield.
Yeah, he had
MIT
a
group,
few
okay.
initially, but like famously, he didn't like talking about the game of life. Like he invented it, but then he was like, just toys, not for him.
Oh,
What InnoMed is.
Hmm?
It's cool.
yeah. So we interacted with Dave Green helped us, and then Matthias Murzin actually, he responded to my Discord message basically.
Cool.
Yeah, so another thing we can look at is not just like distribution across people, but also which parts are getting used over and over again within the patterns. So this is showing the frequency of the use of a part within a system or within a pattern, and on the x-axis is the rank, so the most frequent to the least frequent. And similar to the winner take all effects with like people, you see that there's this group of parts that just keep getting used over and over again. So this is like the R pentomino, and this is the strict still life. And we can look at that over time. So what this is showing now is the red it's showing the number, it's showing patterns that were discovered completely with new parts. So there's no reuse of old parts. And the blue section of the bar is showing the patterns that were discovered reusing old parts. So it's kind of like what this means is in the early 70s, you have a bunch of completely new kind of patterns and discoveries getting made. And then, but past that point, most of the discoveries are kind of using parts from the past. So I think about it like I feel like it's maybe similar to how in the beginning of early life, you have kind of like a lot of completely new systems, and then everything kind of gets built on top of something like DNA, or like in the software like revolution, you have a bunch of uh, competition early on for which software systems are going to get used, like between Microsoft and Apple and Google, and then from that point, all the software beyond that kind of gets built on the winners of that early stage.
So
Because it's just
it's patterns versus components.
yeah. So okay, so it's just total patterns,
Mhm.
and all it's saying is the red ones are ones that have parts that were, or sorry, the blue ones are ones that have parts that have been seen before, kind of.
Got it. Cool.
Yeah. Yeah, I really like this one. So kind of the conclusion that Stephen comes to in the end is just that because looking at this case study, we can kind of formalize what is an engineering system, and based on these kind of models, we can get a sense that it's like taking this system like the game of life cellular automata that has a lot of computational irreducibility and a lot of potential for interesting behavior, and kind of putting the bounds on that to get it to achieve human objectives. And this is just a really nice, kind of visualization of that idea. And I think, using that kind of formalized idea for an engineered system has the potential to like take, for example, give insight into something like computer security, where it's like what happens when you take an engineered system outside of the bounds of what it's meant to do. And I was actually hoping to I wanted to try to do some live coding because it's more exciting. But yeah, so maybe we can do that after as well. But
Yeah,
yes.
that was like one of the discovered ones where they like somebody like kind of put it in a cage or something to try to get it to do what they wanted or something.
Yeah, so this particular guy is a RP129 R pentamino haslett. But yeah, I actually don't know exactly what this one is meant to do. I mean, we can just look at what type it is.
Is it repeating?
Yes, it is. So yeah, let's just see. So I'm just gonna do this. Yeah, so what's nice is all this data is now just on the, Wolfram data repository, so we can just look at these things. Or people can just look at these things. Yeah, so this is an oscillator of period 129. So that's kind of what the goal is to get it to oscillate, Eric. Yeah. But I guess I'll just wrap up and say thank you to, obviously Stephen and Ed, who's like more of an expert on the game of life, was really helpful. And as I mentioned, David Green and Matthias Murzin, we reached out to them, and it was kind of cool to interact with someone who's actually made discoveries in the game of life. But yeah, thank you guys for listening. And yeah.
Cool. We're gonna do some experiments.
Yeah, so I was
yeah,
interested in.
I want to see what the Hassler is doing, and
Okay. So maybe we could use code here.
I'm guessing that the motivation for it was to, try to make something that repeated with that number of time steps.
Yeah, usually that's what it is.
Is that just an arbitrary objective, just to set a challenge for somebody to do something specific? Or is it
Yeah.
in trying to build something larger they wanted to do this?
Usually it's like, I think one of the like kind of challenges is making smaller and smaller patterns that achieve some objective. So like the smallest possible period 9 oscillator. Yeah.
Wasn't it, I think only somewhat recently that they were able to get all possible periods because like once you get to a certain size, there's like some machine that can do all the periods larger than that, but then a bunch of the ones below that they were trying to fill in for a long, long time, right? So
Right. No, that's
And is that just to create any size object that has that oscillation, or were they trying to get it below a certain size?
I think I'm pretty sure they were trying to get just any size. Some oscillations were really hard to get to do with any size, but yeah, then there's always the challenge to find a smaller one, I think so.
And an oscillation here would just be a full repeating of the entire pattern, or something
Yeah.
else. Yeah.
Yeah, the pattern totally repeats itself, right? So
yeah, Stephen mentions this idea of being able to figure out something about all the possible oscillators. Just looking for it. Yeah, so maybe this is it. It was actually found possible to extend it for any period to a construction for guns for any period, or at least a period above 78. Hmm.
So that was the threshold that they could do it above.
Right.
It's more recent than I remembered.
Yeah, it was funny. Like as we were writing the post, they were making discoveries and we had to like edit it.
That's funny.
Yeah,
Yeah,
I
it's
think
interesting. Like my question is related to how in mathematics sometimes you have just constructing things for the sake of constructing it based on just some arbitrary objective or challenge that presented itself. But what's interesting with this blog post was the meta engineering concept where you have sort of dedicated efforts of building these things up for some objective sometimes. So I was wondering to what degree is this like construction to engineer some ultimate goal versus sometimes just being like, oh, let's see if we can make it oscillate 3 times and have a size of less than 10 just for funsies. That's what I'm curious about.
no, I get your point. And I think most of it has been for, as you said, funsies. Um, which is kind of why I think Stephen and seemingly many people are kind of like, what's the point of this whole thing, right? Uh, I think going more in the direction of like actual usefulness, there has been things like this, for example, which generates primes. Um,
Oh, interesting.
but
I
yeah,
guess I guess that's doing this Steve Verasosity like under the hood.
let's see. In effect, it's running a sieve in which all multiples of all numbers are instantiated as a stream of gliders.
Uh-huh.
Let's see what it is. Oh yeah, I mean, yeah, so this is just a cellular automata that computes primes, but actually I'm not familiar with running a sieve. Dugan, do you know what that means?
Yeah, so it's like you have all the numbers and then you take like two and you use two to remove every even number and then you use three to remove every third number and so on and so forth. And then the ones that don't get removed are primes.
Hmm. Okay, that makes sense.
Yeah, there were other big projects, I think that bigger projects where they were building on top of other stuff, like trying to implement an actual Turing machine, like with an infinite tape, or like there's the meta cell where you can get it to make a larger cell out of like
Yes.
sliders that can do any cellular automaton or something. I saw this cool website. I have to try to find it where you could like zoom out and it'd be like the game of life built on top of the game of life. And you could zoom out infinitely and like it'd be like another game of life. And then that would simulate these big cells that would zoom out and uh
Yeah, I've shared that on the Discord before.
yeah, that thing was really
It's
cool.
really incredible. Yeah. I think it got me really into the profundity of some of the stuff for Game of Life was when they could create an object that could recreate itself, like entirely. That's when I was like, wow. I mean, it's definitely Turing complete, right? So, um, did they manage to create that Turing computer in Game of Life? Did they succeed with
Yeah,
that?
so it says, and indeed structures like these have been used to build all sorts of things, including, for example, Turing machine emulators and also an emulator for the game of life itself, which this 499 by 99 pattern corresponding to a single emulated life cell. So obviously it's not very efficient, but yeah, this is supposedly
So
a
that's a cell. That's
single
the
cell.
entire cell of one Game of Life cell. Wow, that's so interesting. So that's basically the encoding of the rule
Right.
for Game of Life.
Oh,
You
wait,
could get
what?
other rules to work on it too, not just the game of life within itself, but you could do other CA too, right? I think.
Not sure, but it seems like it.
Hey, go to that link I posted in chat, the
Yeah, sure.
comparison one.
Ooh.
Yeah, so you can like zoom in and out to see the
So
structure.
now it's cells,
This is-
gliders, and then some gliders, and then
yeah, so it's the same every time. I think so, yeah.
Yeah, so you have all these like structures
Just perfectly
that.
recursive.
Mhm. Here, can you slow out? Can you zoom out very slowly? That kind of have a low frame rate on Zoom
Oh,
here.
okay, sure.
Yeah, so all these squares are being lit up by gliders, and
uh,
that's cool.
I think that's just the speed of the machine in at the bottom right. That's controlling how fast the Game of Life is working.
Oh yeah, yeah. I can animate.
Oh, okay. I see.
Yeah.
All right, I guess I could do like this. And then slowly zoom.
Set it to 1x, and then zoom. Okay, now start like zooming out.
Yeah, so what's happening is
Slowly.
it's speeding up the more you zoom out,
Mhm.
because otherwise every time you go up a scale, it'll be too slow to witness what's going on there, which is an interesting concept.
Oh,
So
I
the
see.
smaller, the more zoomed in you go, the faster the things are going to move, obviously.
I also heard about a thing where some people implemented Tetris in Game of Life. I think they use the cells to do some cellular automata that's better for making circuits, and then on top of the circuits they built Tetris. So
So they built it in Wire World. Maybe we should talk
I
about that
think
a little
they,
bit.
I think they did something like, yeah, like build Wire World on top of those meta cells, and then Tetris on top of Wire World, something like that.
Hmm.
But that's something we should talk about too. Brian
Yeah, actually,
Silverman here
before
created Wire
before
World.
moving away from, before moving away from Tetris, Stephen forwarded me an email that said that somebody figured out how to make Tetris universal, so you can implement life in Tetris.
That sounds
Interesting.
like a fun recursion game. So you do
Yeah,
Tetris in Game of Life, in Tetris in Game of Life. So meta. I shared a link here. Willem, I don't know if you want to open that quickly. It's kind of interesting.
Yeah. Let's see.
So we go
So
down
what-
a bit, actually shows the logic gates that they constructed.
Okay.
Oh wow.
We have like input coming in,
Hmm.
and then based on the logic, it'll output kind of a binary true or false sort of structure. Yeah. I mean, with that, now you've got a computer.
It's like a more direct way than trying to implement Wire World in meta cells, it looks like.
well, it turns out that early on, Conway wanted to be able to prove that it was universal, and he wanted to do things like this. And what he found, and maybe this talks about it, is the gates are relatively easy. The routing isn't. Just turn a glider string down around the 90-degree corner. Needs a bigger structure than to do and or not.
So I guess
So
you can't route a one wire over another if they cross paths, kind of thing.
Well, you can't unless you build a wire cross structure.
Uh-huh.
You have to be able to turn the wires, right? That was a hard thing to do, right?
Yeah, that was the hard thing to
Mhm.
do, which was sort of the genesis of Wire World. I thought if that was hard, you could just cheat and make it easy.
nice.
Cool, you made Wire World.
What up, please?
I mean,
I want
do you have any links to like what the implementation in Wire World or?
If you just Google for Wire World Computer, it's usually at the top. And it's a guy named, yeah, that. And near the bottom, there's a link to the completed design.
Uh,
And I didn't do this. And when I saw it, I thought it was jaw-dropping because this is the stored program computer figuring out primes.
Oh,
Oh.
and displaying them in a.
And displaying them.
so where is it displaying the up here?
Yeah,
Literally
he
makes
managed
sense.
he managed to make, just digit displays out of Wire World cells.
That's insane.
The thing that bugs me about the Turing complete Tetris thing is that it needs an infinite like Tetris horizontally, whereas I feel like it might be possible to make a Turing to make it Turing complete with finite horizontally but infinite like vertically, where um lines getting deleted is part of running the program. But anyway, that's a little off topic.
If that were the case, doesn't a Turing machine need an infinite tape to be a Turing machine?
Yeah, but if you had infinite verticality, like that one's infinitely wide, but if it were finitely wide but infinitely tall, I feel like it could still be possible to do it that way, and it would be neat.
Hmm. Yeah, I'm not sure what you mean, Eric. Sorry.
Okay. Well, it's to do with the Tetris Turing complete thing, so I mean it's not really related that much to this stuff. So.
Okay. Well, maybe
So,
I'll
yeah,
go through really quick
today we're playing Conway's game of
what I had in mind for the live coding, which was I was curious what happens when you perturb these. Like we did a lot of work perturbing the adapted systems, but I was wondering what would happen if you perturbed engineered systems and like if you just change one bit in the initial condition, for example. So I kind of want to show you guys that. But okay, so let's use, yeah, so we need an example pattern. Does anyone have a favorite pattern? I'll just use,
How about the original glider gun?
okay. So that would be, okay, so we can just take these initial conditions and then we're just going to get the rules for those. And then we're just going to try, see what happens if we delete a random one. So I should probably do this.
I guess you could random sample.
Yes. Okay, yeah, that's a good idea, but I'm just going to stick with this.
Sorry, just one other thing about the Tetris thing. In the Tetris thing, they tell you where it's basically they tell you where you have to put the pieces. It'd be interesting also if there were one where like the only way to solve it is by following a Turing machine or something, because they've showed that for like games where they've showed that there are games where you can get in a state where the only way to solve it is by following a Turing machine. It's not just like telling you where to put the pieces. So
Hmm.
anyway, keep going.
Sorry, it's hard for me to multitask, but okay, so then we can just take, yeah, so we can just like see what happens, for example, to the final state. So I guess we can just do this. Yeah, like that. And then we're just gonna do this. Yeah, so this is like, again, just basically taking, making single bit changes to the initial conditions and seeing the resulting pattern. So let's see. What happened? It's weird. Oh, huh. think it's working.
Well, it's not deleting anything from that.
It's not? Oh, wait.
Oh, wait,
Should be.
never mind. Oh, I see. Random integer. Okay.
Hmm. That's weird.
No, I was wrong. Probably right.
I know, but it's still not working.
Hopefully it's not deleting the last, like, case.
Hmm. I got it working before, I'm not sure.
Well, wait. Oh, I see.
Help. Well, let's just try doing. Oh, okay, I know, I'm being stupid. Okay. So yeah, we can just do like, oh yeah, we should probably just enumerate all the changes, but yeah. Yeah, so like these are what happens if you change one rule in the pattern to the final condition, but let's look at the 3D plot. It'll be easier to see what's happening. Hmm. Oh, this okay.
Longer.
Yeah.
Oh, interesting.
Okay, so let's do a bunch of these. Yeah. So, okay. They're kind of like we could think about these as like yeah, like attacks to the system, but it seems that interest some of them, still do their thing. Yeah, we can
What's the
do like,
original thing that happens to it?
oh yeah, okay.
Oh, it's a glider gun, right?
Yeah. So this is what it's supposed to look like.
I see.
Yeah, so we can do cool things like we can look at, if there's any repeats.
I guess that
Well,
the ones that are
it's-
broken rejoin the original one after a few steps.
What do you mean?
You added a cell, and somehow that adding a cell manages to not change like the fourth step.
Hmm.
well, here we're removing a cell each time. We
Yeah,
have
sorry if you're removing one, but it may have some ability to heal itself.
Yeah, that would be interesting.
Well, can you just is there an easy way of picking out the ones that are still working right? Probably so, because those would be the ones where the bounding box got big. Like if you looked at the final bounding box, the
Okay.
ones, yeah, the ones where it's still a glider gun are probably there, the biggest ones.
Yeah, I mean, we can do something much more caveman-like. So it looks like, at least by that, they didn't change. But maybe, yeah, it's kind of hard to tell, but I guess I can just look at the data. Or maybe how about the last frame? Yeah.
I'm gonna drop off, but before I leave, I wanted to share this Game of Life thing, which is the thing I like the most. It's I think they call it the Methusta, with the idea being the smallest initial setup that can create the biggest amount of expansion, sort of like possible.
Like the art.
This is called the Acorn, and it's only a very limited number of starting cells. But if you run this, it creates a like expanding universe that basically pretty much goes on forever. So it reaches a sort of a stable state after a very, very long count. But then it starts shooting off gliders, which theoretically means it will continue to expand forever. So I just thought it's really cool that you have this very, very dense initial, almost like too simple pattern to possibly produce anything too complex. But yet this creates this like unbelievably complex emergent universe. If you speed that up quite a bit, you'll see it just keeps going and going.
I mean, the
So
art.
I just thought that very inspirational.
The Arpentomino is even smaller, and it's like really small, and it goes on for longer than you'd guess, I feel like. Or is it the F?
For sure, but much less long than this. Like the Arpita, I think it goes on for like less than 2000.
I gotcha.
This is around 10,000, but those little guns that shoot off means that this thing will just keep going. Although it stops interacting. Yeah.
I see.
So at this point, it just becomes like oscillators, but those guns that got shot off are going to continue.
So it's like
think
Langstroms
pretty cool.
and in a way.
I think that Arpentomino shoots off gliders too. Anyway, but
Very
Do you
cool.
want to just run it? It's there.
Yeah.
Just do the
If you hit lexicon
Arpentomino.
and then you can search.
Oh, the Arpentomino from here.
I feel like I've heard it called both the R and the F pentomino. I don't know.
Just hit Control F.
Try it.
Yeah, there it is.
You can just click on the button itself. Yeah.
Yeah, there goes some gliders.
Yeah, which is very cool. So it's such a small little initial thing. Nice.
Yeah, but then it settles down.
True.
Yeah, I think I just did a search for like the smallest by the largest possible, which is kind of arbitrary, but that I think Acorn is currently the prize holder for like the smallest that produces the most amount of interactive steps going forward. But smallest is also arbitrary.
It's all arbitrary because I think I agree with Eric that the Arpentomino was, I thought very, very interesting because it really is nothing.
Yeah.
Yeah, that's crazy. Very nice. Okay, I'll catch you guys the next one.
Yeah.
All right. Take care, James.
Yeah, so maybe I can just can keep trying to figure this out. Let's see. Yeah, so we just want to see the ones that are normal.
What do you mean by normal?
The ones that didn't.
Oh,
the
the
last-
perturbations that still retain a glider gun?
Yeah, the last state is the same. So let's see what happened to me.
Yeah. Jay in on chat here once is asking
Oh.
that very question. It's like,
Okay, here we go. So now, yeah, so this is what we want. And then we can do array. Okay, and then we could just do counts. So, well,
you're getting like the last or the nth frame. Seeing which ones
yeah,
are,
so this is
still have gliders on them.
the nth frame. We need to look at the last frame of normal though. let's see. Yeah, but it looks like, well, hang on. So this is the normal. And then I guess we can look at position of,
I guess you could just get the size of the final array. And if it's the same size as the original, that means like at least the first glider like got out to that position.
yeah, but I kind of want to see if it's exactly the same.
Okay.
There we go. Okay, so it looks like these ones didn't, if we do, yeah, I mean, it's gonna be kind of stupid, but right. Yeah, so it looks like some of the perturbations actually, at least by measuring the last frame, don't.
Right. And I would guess that by the, say, the 10th frame, if they haven't diverged.
Well,
Okay,
hold
let's
on.
check that.
Does seem
No, because once they're the same, they're going to stay the same. The question is how many did they have to go before they joined the crowd?
Right.
Right. And I would suspect very few, because if it wasn't very few, the probability of it breaking the thing is quite high.
1, 2, 3, 4, 5. Yeah, so seems like, I'm not really sure what that means. Because why are these all, they seem like they're all different ones, you know?
Well, are these the initial conditions for the ones that are still shooting out glider guns?
This is the position of the perturbation. Oh, well, I know what's in because I didn't see the randomness. But we can just enumerate all the possible changes. So let's do that.
Yeah.
Instead of doing, we can just do this.
Have you tried doing this before, Willem? This is interesting that they can heal themselves.
I was looking at it a little before, but not much. Okay, so what do we want to do? We want to get, yeah, we just want to do, oh, well, that was a stupid way to do it. Should just do this. And then we want to get like this length.
How surprising is it? Gosper didn't attempt to minimize the number of cells.
Brian, have you met Gosper? He seems,
Yeah,
presumably he was.
yeah, but I haven't met him 2 or 3 times all a long time ago.
Got it.
Wait, so you're removing cells? I mean, you could try adding cells too, right? You could generally just like flip a bit or something.
Yeah, I was looking at flipping bits, but a lot of times it actually just does nothing, which is kind of boring.
Yeah, because there's probably half the bits that you can flip, they'll just die out in the next generation.
Yeah, exactly. So it's kind of pointless. But okay, so it looks like this is interesting because it looks like
But Willem, did you reach out to Gosper for this?
I think Steven did. I'm not sure if he responded, but
It's like the whole last quarter of it is about Gosper.
yeah. Yeah, he sent like an absurd amount of mail to Steven apparently. Okay, so let's try to see if there's any repeats in this.
Yeah, what's the most cells you can delete and have it still work? That would probably be hard to figure out, but it'd be interesting to know.
Yeah, so this is interesting because it's uh, each different initial condition change is creating a different pattern. So there's no like kind of oh, well, that's stupid because obviously it's taking into the first. So we need to do, we want to look at, I wonder if we can do this. Yeah, so this is after the 10th step, the evolution, and now we want to see if any of those are the same. There we go. Yeah, so Brian, you're right. It's like a bunch of them are just, you could think about it like healing themselves, but they're just converging to the same state. But yeah, also Eric, what you're asking, I agree. So let's try to look at if you guys are interested, let's look at instead of just one change, let's accumulate changes. So I mean, one thing is we could delete, keep deleting cells. So I need to think about how to do that. Any ideas are welcome.
Okay, so I guess looking at deleting two items.
Yeah, so we can,
When you delete one, you end up with 6 that are the same. Can't you just delete one more from those 6?
so you're saying the ones that don't change?
Yeah, because
Okay.
unless you think that there are 2 that you could delete, that those 2 are different than the one that you could delete.
Well, what about just doing,
Like delete one, then find all the ones that survive, and then delete another one from each of those or something.
Yeah, that's what I was suggesting, but the question is will you miss something then?
Yeah, right.
Is there a 2 that you could delete that each, if you took them each individually, it wouldn't work?
Yeah.
well,
Not getting kind of a large space of possibilities. Well, with just two, maybe not.
Well, how many cells are in the thing?
okay, we should just do this. Okay. I'm not sure. One sec, Brian. Yeah, so we should just do this and then we can just
I've got to go in 15 minutes. Do we want to switch back to a discussion rather than the live coding?
yeah, sure.
Because one of the things that I thought was really, really interesting about the blog post is back in the day, um, everybody but Stephen was trying to do engineering.
Mhm.
And like it's kind of like the world split into 2 sides. One side looking at emergent properties and of spontaneous running of rules. The other side trying to engineer structures. The engineering structure side was pretty much everybody.
Right. Mhm.
Because I know myself, I also, went into the engineering structures thing, by playing the game of, well, like I said earlier, somewhat um, facetiously, since turning corners were hard, I just cheated. And that kind of cheat, when I showed it to Stephen, he just said, "Oh, but that's just engineering."
Mhm.
Right. The thing is along the way there's the other cellular automata role that I did that got fairly well. I was saying that after Conway's Life, I did the second and third most popular roles that were about 10 to the sixth less popular than Game of Life.
Mhm.
But the other one, have you seen Brian's Brain?
I've seen Brian's Brain. It's very cool. Yeah.
Because that's one that the stuff that emerges out of that I found incredibly fascinating.
Brian's Brain is really easy to make gliders, right?
It just that's all it does.
Like all
And and if you watch it for a while, you see that it spontaneously generates glider guns and it occasionally spontaneously generates glider guns.
Mm.
And I sort of thought that I was like making some progress by having examined like 1,000 different rules at the same time that Stephen was examining about a billion.
When was this?
Around 84, 85.
Yeah.
so Brian's Brain was you're Brian behind Brian's Brain. Oh,
Yes.
okay.
Yeah.
Okay.
Yeah, no, I once gave a talk at an NKS conference, and the person introducing me saying, "Hey, who here knows Brian's Brain? This is Brian." Um, I have to say, I didn't name it. Naming things after yourself is like it's not really a thing. Both Wire World and Brian's Brain were named by other people.
Interesting. So,
But to get back,
yeah.
this was just looking at because for some reason the engineering in the Game of Life was the thing that a lot of people did. And when you were showing the list of who did things, it would be an interesting thing to do that for each person. Um, not you're counting structures rather than it would be fun to rate the importance of what they did for each of the things and also to write down what they were trying to achieve. Okay, because Gosper doesn't look like he's number one on the list, but in some serious sense, for the first 15 years of the Game of Life, Gosper was doing most of what was interesting.
Yeah.
And people didn't build on it. And one of the things that you were doing in the paper is just trying to figure out who was building on who and what was building on what. Because one of the things that Gosper did, and this is along a whole other dimension that I don't think that you talked about that much, is Gosper figured out how to get the Game of Life running 10 to the 17th times faster. Okay, so
Wow.
he kind of well, no, the thing that he did is I made up that number. Okay, is
Okay.
before Gosper did his trick, you couldn't run this on more than a like 1,000 by 1,000 grid at about 4 a second. You know, but Gosper figured out a series of basically sparse array techniques, to only compute the things that need to be computed. So suddenly he was able to one of the things Gosper did early on was the puffer train. Do you have that easily accessible?
Let's see.
It should be in the Life Wiki.
Yeah.
And back, yeah, Gosper was making these in the mid 70s, and the ability to run grids as big as this was just no way it could have happened, until he figured out how to do this sparse array game. You
Right.
know, plus some hashing of things that doesn't need to recompute the bigger ones. Plus no end of simple tricks.
Interesting, the
Yeah, I
tail of
agree.
that like fizzles out, and it's not really clear if there's a
Hmm.
periodic structure to the fizzling.
Yeah, but the thing it actually says that right out, the first known puffer in Conway's Game of Life was discovered by Bill Gosper. And he had done other things that were of this category. And what he was doing is he was kind of like Conway himself, as you know, Willem, you mentioned, Conway didn't find this interesting. Okay, that near as I can tell, his motivation, very much like Stephen's later motivation, was trying to show that a simple system could support universal computation. And I don't know if you referenced that in the book. Conway, Martin Gardner did a book that had a collection of papers by people, including Conway, that had a hand wavy how you can show how you can know that it is computationally universal. You know, but the actual practical showing of it didn't happen until decades later.
This is the game of life.
Yes,
CA.
yes. And well, the game of life, and this is the sort of thing that I found very surprising. And this is slightly exaggerated. Moved into the mid 80s, everybody playing with CAs there were people playing with the game of life. There was Stephen and there was me. Now, it's not really true because Langdon was also doing Langdon's Hand, and there were some other people who were trying to construct, you know, the von Neumann automata. But since in that paper you kind of pointed out all of the energy that was thrown into this, and the thing that I think is sociologically interesting, very little of that energy was thrown into pre-NKS.
Hmm.
And that's why really it's great that you did that paper because I think that the important thing is understanding about, you know, discovered versus invented. And Stephen was totally on the discovered side. So when he finally did this paper, you know, 6 months ago, and he was talking about invented, I was sort of scratching my head, and it was sort of like, A, good, B, what took you so long, right?
Or what paper you're talking about?
The one that this talk is about.
Oh, the blog post.
Yeah, the blog post.
Hmm.
Yeah, it's interesting to me that you say though that a lot of the game of life activity came after NKS because I mean just interacting with the game of life people, they're not always like I feel like and you kind of mentioned this that like Stevens explorations in game of life have really been two kind of different paths for such a long time. And so there's like a little bit of a divide.
Well, it's the thing is, and it's funny though, because if you wanted to unpack that and make up pop theories that are probably wrong. By the way, the things that I didn't say that if I said it, I didn't mean to say it. There was a lot of Game of Life activity before NKS. And when NKS came out, there was a first rekindling of it. And as you were pointing out, the pandemic may have caused the second rekindling of it. The thing that I thought was fairly interesting, and this has got to be something about how people work. For Stephen, it was huge, critically important to be able to have the whole evolution as a static structure,
Yeah.
right? Where for a lot of other people, I think me included, seeing how the thing behaves dynamically was the preferred mode of interacting with it.
Mhm.
And I don't know what to make of this because it's funny though, because the first thing Stephen did when he was getting into 2D is he added a third dimension to make it static again.
Yeah. Well, you can see the trends pretty well in that. I mean, it's a very nice way to visualize it. Um,
No, agreed. But the thing that we're looking on the screen here kind of is, you know, that's tickling a different piece of your brain.
mhm, mhm, for sure.
Yeah, I don't think this one in 3D would be very good at all. And certainly a lot of the 3D ones that we looked at, you can't tell what the hell's going on, you know? So I guess it's like a different case, different tool kind of thing. But yeah, coming back to the difference between the game of life and Stephen's work. So would you say, Brian, that like do you think NKS, I guess what I'm asking is, do you think NKS inspired Game of Life work or no?
I don't know. I would guess not, because when NKS came out, there was a wave of people, I think, inexpertly saying, Stephen is saying that the universe is a cellular automata.
Hmm.
Right. But he may have even, I reminded him when he wrote the Fredkin paper that the thing in NKS that comes closest to saying that is in chapter 7. He says, obviously, the universe is not a cellular automata.
Hmm.
Right. Because, because the thing is, Stephen ultimately is working with simple programs that turned into the physics project. And the 2D cellular automata, it's a guess. You can ask him. Actually, in the course of this, did you ask him, or did he say why he didn't find the Game of Life interesting in the day?
Yeah, he just didn't see the point of, making all these structures because he's mostly focused on scientific models, I think. That was his reason.
Yeah, that's consistent with what I remember, the way he was acting back then. Because it's kind of what NKS is about is like doing science on the computational universe, right? It's not about doing engineering. And repeating what I was saying about 15 minutes ago, I thought that this is interesting because figuring out how to make things in cellular automata is, I think, new to the Stephen program.
Right. Right. I mean, but he is trying to use it and in a scientific way. But yeah, I definitely think it's an addition.
Well, what's very interesting in this, and did he mention this? Actually, I read this. I didn't reread this for this meeting. Um, the Gosper glider gun was half invented and half discovered.
Mhm.
That basically, I think I think the blog post did say this. Gosper noticed that there was the honeycomb, I think it was called, structure. And if you just beat the two of them against each other and constrained it properly with blocks, then it could turn into a glider gun.
Yeah.
And he in fact programmatically worked out what the relative positionings of the things were. But I've got to run off now. But thank you for this. It was terrific.
Thank you, Brian.
Yeah.
Okay, bye-bye.
Yeah, I'm good to wrap up Dugan also, if that's okay.
All right, no problem. Thank you all for tuning into the live stream. Willem, it's great having you talk, and it was very nice to have an original gangster, OG Game of Life, Brian Silverman, on the call with us too. All right, see you all next time.
Bye.